so this is just gonna be a little overview of Serac. So Serac is an application built on top of MFEM and expanded for primarily engineering applications. And well, let's just dive into it. Oh, there's a whole list of people that have contributed kind of over time. Jamie started this. She got promoted, and so we are carrying on. We are carrying on. So that is what it is. Okay, so what is Serac? And so let's just say Serac is like a sort of an application again for engineering, and it's built on a variety of other lab developed products. So for example, MFEM, but also other things like Axum and Hyper and sundials, et cetera, et cetera. And so we're trying to take these pieces, compose them, utilize them, see how we can use them for engineering applications. And in principle, provide feedback. I think we've done that in the past, but I haven't been here as long. And what things that could be improved. And so yeah, the other goal is to be able to sort of quickly compose physics together to create new applications. The API should be pretty intuitive for engineers to use. So more engineering language versus math language to some extent. And then the other big sort of niche or advantage is the differentiable by design. So essentially we want any input simulations to also be differentiable, so we can do design optimization. So that's sort of like a key focus of the design and of the motivation for the software. Yeah, and it's pretty easy to add new things and try out new ideas. And I haven't been here too long, and I've been able to try out new things. So there's some success there, at least for me. I think other people have built things too, and I'll show some of that later. So okay, so what kind of physics do we do? So we mostly do these first two on the right here: large deformation solid mechanics and heat equation. The terminology is confusing. So there's another code called Smith, which is built on Serac. That's not open source. So Serac is actually open source. So all these other physics mentioned below heat transfer exist in our other code, but they're not open source. Not basically just for historical reasons. Is what it is. So with Serac, you can build these different Serac or Smith. Sorry, the terms get confused. You can build these different components and build these different applications. So I just want to sort of show, in case people aren't so familiar, like kind of equations, mechanics we might be interested in. I'm not hiding the thermal ones as much, but these are slides I stole from an earlier presentation. So it is what it is. Buckling problems, crashes, contact, fracture, plasticity, large deformations, thermal effects, things like this. Really complex geometries that may be hard to mesh or may not be, and things like that. So just really nonlinear problems and also linear problems. Okay, and so I talked about design optimization. So these are kind of like what I would call the forward simulations, right? You're just running a simulation, right? And so if you're doing engineering design, one thing you might want to do is you might want to run a simulation with a set of input parameters. So you have a set of material properties, you have your geometry, and you want to run it through and get some quantities of interest out, like the mass or the stresses or whatever quantities you might be interested in. And the way it's kind of done in industry typically is if you want to improve the design, then you sort of have to iterate on that. You change the properties, you rerun and see how you've done, right? And so it's sort of a manual process. But you can think of the design process as sort of trying to do the reverse map. You're given the criteria, you want to have a certain target mass, et cetera. And okay, can you give me the properties? And so, so this can be done. People do this now. For example, with what I would call black box or gradient-free optimization, where you just do the process I just said. You have no information about sensitivities. You just change parameters until you get lucky. Well, you don't get lucky. You're obviously going to go in the right direction, but you're not taking advantage of gradient information. Other people, are trying to work on ML solutions here. That's not the approach we're taking here. The approach we favor is on the right, these gradient-based approaches. And the theme is that you have a lot of design parameters, not just like 4, but millions, right? Every node can be a degree of freedom. Every material property can be a thing that you can change in your design. And so this requires sort of intrusive changes to codes in general in order to take advantage of this. And they're using this technique, which I'll talk about a little bit, called the adjoint method, which makes this computationally tractable. So there's this slide that we've been giving for a couple of years, where it's like, okay, we're taking the engineer out of the loop, right? You have some, like I've said this before, but you have, your design parameters, you're going to run your simulation, you have some objective you care about, maybe some constraints, and we're just going to automate that process for you. So no engineers. But I'm changing the slide because now that I'm giving the presentation, I'm putting a check on the engineer. Okay, so in my experience is that when you want to do this process, the engineering is essential. And where does that come in? That comes in how you define these objectives and how you define these constraints. Because if you come up with a made up objective that doesn't make sense, you're going to get a really bad design. And so actually a lot of time is spent thinking carefully about what problem you actually want to optimize. And that's an absolutely essential ingredient of this. And there are certain people in our group who are very good at this. And it's really essential to have that kind of intuition. Okay, so this is sort of the same stuff, but basically, what are the kind of things you can do with design sensitivity if we're gonna have a differentiable physics code? What else can we do with it? Okay, so there's inputs, like I said, initial conditions, parameters, loads, run through your simulations, you calculate things you care about. You can do this for design optimization, like I was highlighting, but you could also do this for UQ, accelerating sort of the accuracy of UQ information, model calibration, not just for design, but if you need to calibrate your material properties or other aspects of your simulation. And then generally kind of these kind of under the umbrella of what I would call an inverse problem. So this is sort of just vaguely an example, but you have like nonlinear solid mechanics. This is an application by Jorge Luis's project where he's optimizing sort of liquid crystal elastomer materials. And so what are these? These are like complicated materials which have anisotropy and a lot of nonlinearity. And you're able to print them in different orientations and with different properties. And so the question is, can you essentially print these in ways for the material to behave in really cool ways? That's more or less the story. And so this is just sort of just setting up the idea that you have an equation, you have like a weak form for your PDE of interest. In this case, it's a complicated nonlinear solid mechanics problem. And what are you going to do with that now? Okay. So what you want to do with that is you want to again come up with some objective Q with a constraint A. A is your PDE, maybe other things, but at least it's your PDE. And you want to compute the derivative. Okay, essentially what is the minimum of your quantity of interest subject to that constraint? And as a piece of that, you're going to have to compute sort of gradients, right? So you're going to have to take the sensitivity of your quantity of interest plus the sensitivity of U with respect to P. Now this is kind of really tricky to compute. You can do it this way. It ends up sort of scaling poorly too in terms of the number of parameters and stuff. But there's this trick that many people in the audience may know about. It's called the adjoint method. There are a variety of ways of deriving it. This is one way that's taught in class sometimes, where you construct essentially the Lagrangian with your quantity of interest. Plus you have this constraint which you want to be 0. So you hit it with a Lagrange multiplier. And then you say, I want basically stationary with respect to everything. And what you find is will pop out an equation for this multiplier, which you can solve up front. It's a function of essentially the derivative of the thing you care about with respect to the state solution and things like that. And it ends up just being the transpose of your forward stiffness matrix. Anyway, none of that kind of matters. But and then once you have this multiplier, you can then compute the sensitivity of interest. And this is very efficient. It doesn't scale with the number of unknowns. It only scales with the number of state variables. So it's essentially as expensive as your forward solve. There's a lot of caveats there, but you can think of it as basically the same cost as your forward solve. Different for nonlinear and transients and things like that, but whatever. Okay, so this is sort of the high level thing. I have a PDE and I want to take sensitivities of it. Okay, but now what do I do with that? I need to somewhere I need to take a derivative of something. So what does that look like? Well, there's different ways you can take derivatives. This is sort of classic. The classic way, of course, is just finding differences. Like probe one way, probe another way, divide by 2 epsilon, give me an approximation. That's pretty slow. It's not very accurate. The historical way in codes is just to do it analytically. You go into Mathematica, you derive it all. Maybe it generates code for you. That'd be kind of cool. That's a viable option. But the option that we're choosing here is automatic differentiation. And it just means you kind of don't have to think about it as much. It automates the process a little more. But it can be a little bit more invasive in the code. And so, okay, let me see how to phrase this. So I was talking about we have this adjoint on the whole PDE system, but you don't need to differentiate. I just mentioned this morning, actually, you don't need to differentiate on the whole system level. This is things like if you were using like machine learning packages like TensorFlow or JAX or PyTorch, you might write, I've done this, other people have done this, you might write your entire PDE solver in those frameworks, and then using essentially the back propagation algorithms that neural networks rely on, you compute all these adjoint calculations. And so that's one way of doing it. It sort of puts your entire solve into the automatic differentiation, which has some downsides. So instead, it's realized that you can just do this for the most part, you can just do this. You can think about most of the time you can think about doing this just at the quadra point, and then just doing assembly like normal because the derivatives are going to be linear. And so you can do your normal assembly operations and just think about just differentiating the quadra point level. And so tomorrow we're going to hear about DFEM, and so DFEM is trying to use enzyme and automate all this stuff through MFEM. And we're very excited about that coming on board. At the moment, what we have is sort of what was available to us, and there's another classic strategy actually, but this is this dual number strategy where every time you have a value that you're evaluating in a computation, you carry along with it its gradients, sort of stuck next to it, and then all the chain rolling has to happen as you're computing things. If that makes any sense. That's how it is currently now, and then the way that works, sort of from the interface point of view, and thanks to Sam for really like sharpening and making this functional interface, I think, very clean and sharp and making it nice. But the way you can think about it is like, if you want to define a new weak form in Serac, you write code that's kind of like this. You define sort of this residual class, and you have to tell it essentially what the term is in front of these different test spaces. So a source term in front of just the vanilla test space, and then a flux term in front of a gradient space. Okay, and if you're able to write your PD in that form, essentially we will ingest that. That's the right word, and automate the construction of a bunch of stuff. So for example, here you can take if you were just to call essentially evaluate the residual, it would just give you the value of it. So if that if you're doing a nonlinear solve, it'll give you the out of equilibrium residual. If you want, there's the syntax where you can say basically differentiate with respect to an argument, and it will construct you essentially a linear operator, which you can then convert into a sparse matrix, an MFEM sparse matrix, or a hypersparse matrix, really. And so it's pretty much as simple as that. You can sort of construct these different PDs as you go on the fly. So it's quite nice. There's been a recent addition it's been a common request of our customers that a very common thing we always do is shape optimization, topology shape optimization, material property optimization. But shape optimization comes up a lot. And so you can think like you kind of have to do the same operation over and over again, right? If you want to compute, you have an initial mesh that's read in, it's in a certain configuration, and you want to really warp its shape to a new, during your design process to another shape. You think in terms of the what's so-called shape displacement. So it's how much your geometry is warped. And when you do that, of course, now you have to essentially chain rule in order to compute all the physics on the actual deformed shape by P, not on the reference shape X. And so shapeware functional takes care of all that for you. So you don't have to think about any of those transformations of spaces. It just sort of behind the scenes does all that. So it's really just a convenience thing to sort of wraps some of these inconveniences. And so how this might work in this case is that there's another example of using, in this case, shapeware functional. Instead of it being a weak form, this is actually a double. So in other words, it's just evaluating a scalar. It's just so actually functional. And it inputs, for example, the shape coordinates, the form coordinates of the geometry and whatever field you want. And then basically the syntax here is kind of similar. You define what you're integrating. In this case, you're just integrating the parameter of the domain, and you take the derivative of that quantity of interest with respect to shape. So essentially, it tells you like how the integral of that field changes as you change the shape of the node. It's basically the nodal coordinates. When I say shape, I basically mean like you're moving all the nodal coordinates, and it tells you about sensitivities. Okay, so we've had some success, I think, in by using this infrastructure built on MFEM to deliver sort of pretty quick turnaround results for customers. So this project I mentioned earlier by Jorge Luis, where it's doing this liquid crystal elastomer design. So again, he has very complicated material models at each quadra point. And he's able to essentially tune their orientations and properties in such a way that, under a temperature stimulus, like say you raise the temperature, depending on the orientation of these crystals, they'll expand more in one direction than another. And that'll cause sort of a large deformation and very unintuitive warping. So it's like, this would be like impossible to do by hand because certainly I would have like almost no intuition as to what like some anisotropic straining would do to the geometry. But, through this process, you're able to say, oh, okay, I want it to do this when it's heated up. And we're able to design for that kind of a objective. Then we have a sort of like, this is like a multi-physics application. We're optimizing electrodes, like for use in batteries. So there's like shape optimization and results like topology optimization for electrodes. And the key is just that these are like not just a single equation, but a coupled system of pretty sophisticated equations that you basically type into this functional framework, and it's not as simple as what I'm saying, obviously, but it's it's relatively simple, like to combine these physics and get a new application up and going. So this does take some work, and we're actually working on making that easier. So we're excited about that. All right. So another application is freeform shape optimization. Like I mentioned, a big application is like you're changing nodal coordinates and you want to optimize the shape of a design. It's similar to the talk from this morning. In this case, this is an application where you want to say minimize the mass, make the lightest thing possible, but you don't want it to exceed some stress criteria. And so, so again, this was run through Serac, and Kenny's done a lot of work on essentially coming up with sophisticated ways of constraining the design space. So, for example, like on the top surface here, this connection needs to stay parallel and fixed to the top, but it's allowed to slide along the top, and then a similar constraint here. And then you have sort of like a bolt hole, which has to sort of maintain its shape, but it's allowed to move. There's a little movie, finally, where you kind of see an example of like this design optimizing in real time. You can see it's allowed to move, but it has to stay fixed and flat, and the bolt hole is staying circular and translating, but not changing fundamentally much more than that. So, yeah, this is just an example of sort of the things you can do. And he does this through these approaches called filters. And anyways, there's a lot of background, but it again. All right, and so then I want to do like a quick shout out to Lido. So Lido is sort of the sister code to Serac. We both have sort of independent lives, but a lot of these combined optimizations happen together. And so what is Lido? So I mentioned sort of Smith/Serac. Sorry, the terminology is confusing, but it's what I've been talking about. It says Smith. Owns the physics in some sense and owns the sensitivities through the physics. Lido is essentially a graph library that's, amongst other things, that's able to sort of compose physics together. So if you have a filter, which is a Helmholtz filter, that's a certain PD solve. If you have another part of the physics, which is a nonlinear elasticity solve, for example, you call through to Serac. But Lido essentially builds the computational graph of, I need to do a filter, I need to solve a nonlinear equation, I need to average stresses over this part. And so Lido holds this graph and evaluates quantities on the graph, and then is able to backpropagate sensitivities through the graph, just like neural networks in some sense. And then both of these codes depend heavily on MFEM, and it's sort of the common abstraction that we use to exchange data between Lido and us. And so that's sort of how the infrastructure works. This is just sort of a simple example of what a Lido graph might look like. This is a non-trivial one, but the idea is you might have certain inputs. Then, like I mentioned, this idea of a filter. You can change the geometry through a filter. That's some topology optimization related lingo. Apologize, but it's basically a PD solve. And then you might even call to essentially a machine learned model at some point. And then maybe later on you go back to us. Like, oh, I want more physics from you guys. And this is all just built up on the graph. And the output of these things from the graph might be the total mass, which might be your constraint. And in this case, the compliance, it's a measure of compliance of the system, which might be your objective. So like minimize compliance subject to a mass constraint. And so this is what the graph for that might look like in Lido. And this has been used successfully to get in some cases, some pretty quick turnaround times on some things. This is an example of a negative thermal expansion problem where your goal is to, well, it was basically a concept brought to the team, and within a week they were able to get a prototype design which was able to achieve the design objectives. So a lot of these pieces were kind of all together already, so it helped. But the point is, it's been useful in quickly getting new concepts out. Oh, apparently I'm rotating it.
It's the base materials in there only expand, right?
Yeah.
With temperature, but the net thing shrinks.
Yeah. Each individual thing can expand, but the overall system can contract because of the sort of weird network of mechanisms occurring. And there's other examples. I won't really go into, but it's been used for a few things. Other shape optimization, linear resonance. There's actually a lot of applications now. This is like kind of out of date stuff, but it's not going to show a ton more here. But yeah, we're trying to build up just our capabilities and more examples as we go. More recently, this is not an exciting image, but it's an important capability. Most of the things we've focused on in the past have been static problems, and so now we can actually do transient adjoints, so we can compute a dynamic problem and back propagate through the entire transient thing. So this is an example of a thermal transient problem. We're doing essentially a manufactured solution, making sure that we can design optimize back to what the known solution would be. There are actual other real interesting dynamic ones, but we can't show them yet. I think those will come later in the year. We'll be able to present more of the cool dynamic problems we've been getting going. Anyway, oh yeah, okay, yeah, getting the right temperature. It's great. All right, another thing to mention is that we also build, we also utilize Tribal. So Tribal was mentioned before. It's a contact library built on MFEM as well, and these common components are helpful. And it implements primarily for us this mortar contact algorithm, which is sort of a maybe state-of-the-art in engineering contact enforcement in terms of stability and reliability. And actually, Eric presented last year on this. He was, I think he's online. I saw him a second ago. He presented on this re-decomp thing where you can essentially, in parallel, as things evolve, you can re-decomp where the contact is happening. And you can kind of see this here. I have a cool problem where you have ironing, and as the system evolves, the re-decomp can decide to repartition where the contact needs to happen for the best efficiency. And so, again, Eric presented on this. This is like a callback to last year, really. So I wanted to point out that we depend on that. And so we're really excited about this. This is for forward problems, and we are like actively getting all this working for back propagate the sensitivity, right? The gradient calculations. And so that's in flight. And there's other projects around the lab that are also working on convex sensitivities, and we're learning a lot from them. So it's going great. With the last bit of time I have, I want to talk kind of more about like kind of my pet project within it, which is sort of around solvers. And so it's really awesome that MFEM supports sort of interfaces, especially through Hyper, but also we've been plugging into PETSI recently, although now we're kind of back to Hyper most of the time, but, but it was good to try. And so, yeah, anyway, so for these for certain kinds of really complicated problems, like I show on the right here is the buckling problems. If you just use like Newton's method or even a line search, like it just will not solve it, or even express it. It just doesn't work. And so the way in which we resolve that is if you think in terms of instead of trying to solve just for equilibrium, right? Because if you just solve for equilibrium for a set of equations, you can find unstable equilibrium. You can find like quasi-stable equilibrium. And so instead, if you're able to formulate your problem in terms of minimization problem, you have a lot more structure. And so most of solid mechanics can be formulated that way. Even if it's not, we have ways around it. But but conceptually, if you think about minimizing energy, you're able to be way more robust. Since you're not just solving for equilibrium, you're solving for a stable equilibrium, which means like the eigenvalues at your stationary point have to be positive semi-definite. So this is just quickly going through some examples. Well, apparently not. This is just Euler buckling. So you have a long beam, and if you put a load on it, it'll just compress really boringly. And then all of a sudden, boom, out of nowhere, one step. And so this isn't run like dynamically, this is quasi-statically. Just showing that, even though there's a big configuration change, you can handle this totally reliably. You don't have to like subcycle or anything. We happen to be using a trust region solver. That detail is maybe not, we found a lot of advantages to that, but there's other ways other minimization algorithms you could use in principle. This is one of our projects. We're trying to design mechanical logic gates. And so here's an example, again, quasi-statically, where you essentially push the problem in. Oh, it's not going to be what I want it to do. It's going to go really fast. Anyways, you push it in, it buckles one side or the other, and then you take that one side and you push it with a force. And then at some point, as it's coming across here, boom, it's like a massive configuration change. And essentially this is not solvable. We haven't found any other solver other than sort of minimization algorithms that can do this reliably. That's how I'll phrase it. So we're excited about that. These are sort of other more complicated examples, collaborations with some people at India, doing sort of snap through of like multi-layers of these like buckling mechanisms to like dissipate energy or other things you might want to do. And again, success with these solvers. And then this is like the one I kind of made this one up because I put a lot of work into getting this. Well, you'll see. Anyway, so it's kind of a goofy problem, but here's the idea: is that we punch it in. Well, we'll just play it fast first because there's just too much going on. But basically, no, that was the wrong one. Sorry. That was the end one. Okay, so this is a frictionless one. And so what is going on here? The first step, basically, take the plate, push it in, it buckles. Second thing you do is you pressurize it and it buckles all the way through. Essentially, none of these steps can be solved with any other solver. And then all of a sudden, for no reason, like a bowling ball just comes out of nowhere and it's going to hit this thing, right? And it's going to kind of push it, and then it's going to sort of snap back, and then it's going to push through. Anyways, it's just a goofy thing. Comes through, it snaps back, and then when at some point actually it reaches to the point where it's getting into this like other bistable, sort of a bistable well, this configuration, right? It's either flop this way, right? If you have a piece of paper, you flop this way or that way. And so at some point, if you press it far enough, it just barely makes it and it just pops all the way over by itself. All this is quasi-static, right? Running this dynamics isn't a problem, by the way, right? You can do this with a dynamic solver, but quasi-static, this is really quite tricky to do. Anyway, so that slips through. And so then I added friction just to see what would happen. And basically, it's just kind of funny to see, like it slides over, it gets pinched off here, and then now instead of slipping through it, it's actually able to stick and stretch it all the way out. And so anyways, I don't know what the engineering value of this is, but I thought it was fun.
Playing some bowling balls.
That's right. So, okay, so I can wrap up. So these are future directions. I think like the main ones, sort of just making it even easier to use, maybe more extensible, and then, differentiating contact, because every application almost every application for solid mechanics involves contact. So it's just a huge focus for us. And so we're excited about the developments there. And anyway, you can read the rest if you're interested, and I'll take questions.